All right, so it says we need to drive 40 kilometers east in 32 minutes. What will your velocity be in meters per second? Okay, so we've got a couple options here. Do you think it's easier to solve for velocity in kilometers per minute and then convert, or just convert them first? I would convert them first. We don't have a quick change between kilometers per minute to meters per second. We've got a quick change between kilometers per hour and meters per second. So I would convert them first if it was me. So if I'm going to go 40 kilometers east, that would be my displacement. So instead of 40 kilometers, how many meters is it going to be?
40,000.
Right, 40,000 meters. Okay, because there's 1,000 meters in a kilometer. And then 32 minutes would be my time. And how do I convert that to seconds? Yeah, just multiply by 60. Okay, just multiply by 60. So 32 times 60 is 1920 seconds. And so now I'm able to solve for velocity equals distance over time, right? Really, we know it's delta x over delta t, but my initial displacement is just 0, right? It's where I started from. Same with my initial time. So there's no need for me to really put in that delta. I'll just say that velocity is equal to 40,000 meters over 1920 seconds. And I'll get a velocity of 20.8 meters per second. Okay, but I'm missing one thing off that answer. 20.8 meters per second. What am I missing if it's velocity? Have to have direction. Okay, so since it gave me a cardinal direction here, I need to include that cardinal direction in my answer. If it doesn't give me a cardinal direction, if it just uses positive or negative, then I'm fine with leaving my answer positive or negative. But if it does give us a cardinal direction, we include that in our answer as well. Okay, so there is my answer in meters per second. Now it asks us for what's my velocity in kilometers per hour. Okay, it's on your slide, but I'm not going to move forward and erase my stuff. So if I want to go from meters per second to kilometers per hour, what's my shortcut? Do you remember?
Divided by 3.6.
Okay, it's 3.6, but this way I'm going to multiply. Right? I usually am going to go kilometers per hour to meters per second, and that's a division. That's the one we'll use more often. But if I want to go from meters per second to kilometers per hour, I multiply by 3.6, right? That's just not the way we use that conversion very often. And so it's 75 kilometers per hour. Remember, I could set up the t-chart 20.8 meters per second, and I would say there's 1,000 meters in 1 kilometer, and there's 3,600 seconds in 1 hour, right? That's where the 3.6 comes from right there. Okay, so if you can't ever remember the shortcut, that will always work, right? The conversion in the chart will always work. We have to remember to set up our units, meters per second. Okay, they don't go on the same side of the t-chart. They have to go in their actual fraction. Okay, question about that? Yep. Oh, probably not. No. Okay, realistically, we've got 2 there and ambiguous there, so our answer should probably be in 2. So I probably should have rounded that to 21. It's not going to be something I really am picky about, but yeah, something we probably should think about at least.
Okay.
Yeah, good question. Okay, now let's look at the difference here between speed and velocity. So we talked about speed is just the scalar quantity of velocity. It does not include what? Speed does not have to include what? Direction, right? Because scalars don't have to include direction. So it's a scalar quantity. So the way we can think about speed is that it's the total distance divided by total time. Write in here that it's divided by total time. And the reason I say that is because if I'm trying to find the average speed of a person that takes a long trip, I have to even include the times like they took a break, right? If they rested for 30 minutes or whatever, that has to be included in my calculation for average speed. So it's total distance and total time, okay? Remind me what the difference is between distance and displacement.
Displacement is
How far it is from point A.
Right. Displacement is starting point to end point, but distance involves what?
The total amount.
Right. Anything it took me to get there. Distance includes the path it took me to get there. So it's total length that we covered. So those two values can be different. Wow, 2 exclamation points. I must have been really, really like excited about that when I typed that in, okay? It has no direction at all, okay? No direction. Speed will always be positive, right? Because for us, the negative indicates direction. It never indicates the, like a negative value. That makes sense, okay? Only a magnitude. It's essentially the absolute value of velocity, okay? In some cases, when our distance and displacement are the same, so it can't be negative. Our velocity can be negative because it indicates direction.
And that's just like going south or east.
Uh-huh.
Right.
Yeah. Negative would be if we go south or west. Negative would be south or west.
Yeah.
It's okay. Yep. Okay, let's look at an example here with speed then. Okay. A car travels with a velocity of 50 meters per second east for 2 minutes. Then they travel south for 30 meters per second for 2 minutes. What was the average speed? We looked at this problem and we looked for average velocity in the first part, right? If you look back at your slides, a couple slides, we did this exact same problem on the velocity slide. So we have some of that information already, okay? Can you look back at that slide there and see what was the total distance we traveled? Right? If we go 50 equals x over 120, what was the distance we traveled for the first part of our trip? Okay, this one was 6,000 east. And the second part of my trip was 30 meters per second for 120 seconds also. And so this was 3,600 meters south. Okay, so if I want to find the average speed, I'm going to take my total distance, 9,600 meters, and divide that by my total time. So what is my total time here? So speed equals 9,600 meters divided by 240 seconds, right? Because I went 2 minutes one direction, then 2 minutes another direction, or 120 seconds both ways. So 9,600 divided by 240 gives me an average speed of 40 meters per second. Okay? So how many of you are like, well, yeah, that's the average of 30 and 50, right? Anybody recognize that?
Oh.
That's the average of my two initial velocities. So I will tell you the only reason that works out is because our times were identical. Right? Speed will be like a weighted average. If I went 50 meters per second for 2 minutes and 30 meters per second for 5 minutes, my speed would have been closer to 30. Right? Does that kind of make sense? I would have traveled a longer time at a lower speed, so my average speed would have been less. Okay, so it only really works out to be a true average when we've got identical time. Okay? Questions about solving that one?
I got lost.
Okay,
Like,
for, which part? This is total distance.
3,000, yes.
So I brought that up and I take total distance divided by total time. So my total time is 120 plus 120. Yep.
Wait, so if your time is the same, is there a shortcut without doing that?
If my times are the same, I could just take the average of my two velocities. Right? 50 plus 30 divided by 2 gives me 40. Yeah. Yeah.
Is there a reason that there's like, is that supposed to be a division bar above the total distance?
This is just adding those two distances together. And I get 9,600 meters.
Oh, okay.
I just added those two to get my total distance. Okay. Okay, and then it asks us, what's our average velocity? To know our average velocity, what do we have to have instead of distance? We need to have displacement. And we solved for that, I think, on our previous slide. So do you have that information still?
Yeah.
What was our displacement from our previous slide?
6,957.
Okay, meters over my time, which is 240 seconds. Okay, so 6,997 divided by 240 gives me an average velocity of 29.15 meters per second. Okay, because it's saying if I was going to travel from start to finish in 240 seconds, I could go a lot slower, right? Because I don't have to make the sides of my triangle. I'm just cutting right across to my finish line. Does that make sense? Okay. We good with the difference between those two? Okay. All right. This next slide here, go ahead and do this one on your own. It is honestly, truly as easy as it seems. High school athlete runs a 100-meter dash in 12.2 seconds. What's her velocity in meters per second? It's literally as easy as it seems. So do that one just real quick. Velocity equals displacement over time, which is 100 meters over 12.2 seconds. And I get a final velocity of 8.19 meters per second. Okay. Do I need to include a cardinal direction here? No, because it wasn't given to us, so we assume forward, right? We assume positive, and so we just keep it at a positive number. Versus time graphs. Okay, if we have motion that is not just simply something goes from A to B at constant velocity, if we have complex motion, then it needs some graphical representation. Okay, so you can use a motion diagram or you can use a graph. Okay, a graph shows us more defined kind of time intervals and things like that, but position versus time graphs in general look like this. Time's always on the x-axis, and then position is always going to be on the y-axis. Okay, so in this particular graph, as time goes on, right, every half of a second, where are they going? Look at this graph right here. At half of a second, how many meters have they traveled? 1. After 1 second, they've traveled 2 meters. After 1.5 seconds, they've traveled a total distance of 3 meters. Or you can think about it as they're 3 meters away from where they started. So in this case, my person is just walking forward at constant velocity, right? Forward would be in the positive direction. If they were walking backward or away from the origin, it would go in the negative direction. So we can have our graphs complete kind of this whole, both quadrants here. Okay, we could use both the positive and the negative quadrant there. Would our graph ever work backwards like that? No, because we can't have negative time, right? For these graphs, we're always going to move time forward. So that means our graphs will always move in the positive x direction, and then the y direction will kind of vary. Okay, so on a position versus time graph, they show displacement versus time, and the slope of that graph is an object's velocity. So I can calculate velocity just by calculating the slope of the graph. Do you remember how to calculate the slope of a straight line? Yeah, rise over run. Okay, or the slope of a line is m, delta y over delta x, right? Change in y over change in x. So really, if you look at it in velocity terms, it would be like the change in displacement over the change in time, right? It's the same, it's a parallel equation there. On the y-axis is displacement, and on the x-axis is time. Okay, so when we calculate slope, that's the equation that we use to do it. Change in y over change in x. And that would give us our velocity in meters per second, assuming that our graph here on the y-axis is measured in meters, right? You need to be careful in case it's measured in centimeters or whatever, but most of the time it'll be meters. So, all right, if I look at the velocity, if I look at the slope of this graph, it gives velocity. So I want to walk through kind of what's happening here with our motion in this diagram, okay? So from 0 to 2 seconds, what's happening in our position? What's my person doing? Yeah, they're standing still. Their position is unchanging, right? They're staying at their starting point. The origin right here would be their starting point, right? If their position is 0 meters, that means they haven't moved. Okay, from 2 to 5 seconds, what have they done? They moved which way? Forward or backward?
Backwards.
They moved backward at constant velocity. A straight line tells us we've got constant velocity. Okay. If we had any sort of curved line, that would tell us that our person was speeding up or slowing down. And we'll kind of look at that in a little bit. But a straight line right now tells us constant velocity. So we stood still, we moved backwards at constant velocity. From 5 to 7 seconds, what did we do?
Move forward.
We moved forward and we just happened to pass our starting point, right? We moved forward and we hit our starting point and we kept going. Okay. Do you think this segment of time, are they moving faster from 5 to 7 seconds or 2 to 5 seconds?
5 to 7.
Yeah, good. Why do you think 5 to 7? That's right.
Because the line is longer and it's only 2 seconds.
Okay, good. So it's a steeper slope, right? We're looking for steeper slope would tell us a faster velocity. Let's see, from 7 to 12, what are they doing? Standing still. From 12 to 14, what happens? We're walking backwards. And are we walking backwards slowly or quickly?
Quickly.
Right, really quickly. We're covering a lot of distance in a short amount of time. Then what do we do here? Forward, then what? Stand still, then what? Forward, then stand still. So where did we end up? We happened to end it up right at our starting point.
Sorry, displacement.
Displacement would be 0. Yeah, good question. Okay, displacement would technically be 0 there.
So it doesn't matter that even though they're in like different like spots.
Mm-hmm.
It's still
Yeah, because all they did was walk back and forth, back and forth, back and forth, and then they ended up exactly where they started. We're going to look at another type of graph that doesn't have that same relationship, but we could not calculate the velocity of this whole graph at one time. Like, we couldn't calculate this person's velocity all at once. We would have to calculate what's the velocity of this time, what's the velocity of this one. We have to do them individually. There's no way we can put that all into one equation. So if we've got a complex motion, which means we're doing different things at different times, we have to solve those in separate equations. Okay, so we could calculate the slope of them kind of one at a time. But okay, if we look at our equation y equals mx plus b for a straight line, y is really our displacement. Okay, I put a d because some textbooks use d, but we use x. The slope of that is the velocity, the x variable is the time, and then my y-intercept is like my initial displacement. It's where I start, okay? So let's talk through what happens here in this graph. Calculate the velocity. Let's find what's the velocity of my person from 1 to 3 seconds. What is my velocity from 1 to 3 seconds? Okay, and so how do we calculate that? Just with slope. Okay, just with slope. Good. Okay, this slope lends it to a pretty easy calculation, right? Because we go up 20 over 1, up 20 over 1, right? We have a pretty easy calculation here for slope. But if we do change in y, remember it's always final y minus initial y over change in x. So we can't do that backwards, right? Our slope has to make sure it matches the direction of our slope. So our slope needs to come out positive because we're moving in the positive direction. Right, we're moving forward. So are we comfortable with that? Calculating slope? Okay, very good. What happens here from 3 to 4.5 seconds? What's happening? They're standing still, okay? So if this is our origin, what's my final displacement then? If this is my origin, what's my final displacement? It'd be 20 meters, right? Because it tells me that I end up at 20 meters from start. Okay? So, anytime I want to know displacement from a position versus time graph, I just read the y-axis. If I asked you, what's my displacement at 40 seconds in this graph? If I said, what's my displacement at 40 seconds? What would you tell me?
5.
What's my displacement at 40 seconds?
30.
Yeah, you would tell me it's 30 meters, right? I'm 30 meters away from my origin at this particular time. Okay, if I asked you what's my displacement at 30 seconds, you'd come up here, figure out where it is, like roughly 20, right? You're kind of just making a guess there because it doesn't intersect perfectly. But for section A on this graph, am I moving forward or backward? Forward. And B, I'm doing what? Standing still. And C, I'm doing moving backwards. Am I moving backwards quicker than A or slower than A? Slower. Good. Okay, so do we feel pretty comfortable with analyzing that position versus time graph? Okay, very good. All right, I'm going to stop right there for today.